Hello, everyone. As Yasi mentioned, I'm Brian Homerding. I'm a computer scientist on the performance engineering team with the Argonne Leadership Computing Facility. Today, I'm going to go over what Kokkos is, give you a kind of a brief introduction to it, and along with the kind of corresponding projects. Then we're going to go through some of the examples provided um, and give you a kind of firsthand knowledge of how to make use of it. Okay, so first up, what is Kokkos? So it's a C++ programming model for performance portability. It's implemented as a template library on top of CUDA, OpenMP, and SYCL. So this is kind of different from some of the other programming models where it's completely implemented with C++ templates, basically using lambdas and also templates. It's aimed to be descriptive and not prescriptive. Basically, you're just trying to say things run in parallel, not run them in parallel in a specific way. It's aligned with the C++ standard. It keeps kind of expanding. It has built-in, well, it has corresponding support for the various math libraries as well as for the various HPC tools that we're going to learn about later in the week and in the future. It's open source. It's available on GitHub. It's also a Linux Foundation project, and it's part of the High Performance System Foundation also. It has a whole lot of users across a wide range of institutions. Just one thing about it being implemented as a template library. So kind of the nice thing based on that is that when you use it for portability across systems, so like on Aurora, you're going to be running this Kokkos programming model on top of SYCL. So in the end, you're going to be running SYCL kernels, but you're going to be working in Kokkos. Whereas when you move over to Polaris, then you're going to be running on CUDA. So essentially, you get to run with whatever programming model is kind of best supported for the low-level hardware, which is kind of nice, but it's sitting on top of it, so you add an extra layer of abstraction. So in theory, it's a zero-cost abstraction. Has a very wide ecosystem. So basically, I have a lot of applications, Trillionos. Then in the main kind of core ecosystem, you have these Kokkos kernels. Those are the math libraries, graph kernels. Then the Kokkos core. This is kind of your GPU or your offload programming model. So this defines like parallel execution and data structures. This is mostly what I'm going to be focusing on, but there is a ton of providing a ton of extra support out there. So with the Kokkos tools, there's kind of built-in support for profilers. There's support where it kind of hooks in with existing profilers to help you understand. There's a lot of documentation, tutorials. There's a whole bunch of videos on everything online. And I put a bunch of pointers in the GitHub README. They're also going to be in the slide deck later. So in that kind of core programming model, you have kind of two main parts, the parallel execution and the data structures. So the data structures are kind of what memory space, where is your memory going to live, the memory layout, how do you want it laid out, you need distributed access, and then memory traits is how you're going to access it through either streaming it, atomic accesses, or restricted access. Then for the parallel execution, so this is kind of what we've been mostly focused on, especially for getting running on GPUs, especially you want to make use of the GPUs for the big systems. So you have your execution space where, there's support for CPUs, GPUs. You can also run on other type of hardware, but for now we're focused for Aurora. You want to be executing on those GPUs to get access to all the performance that's available. And then you have your execution patterns. So this is saying how. So this is kind of like what kind of parallel computation are you doing? The main ones being that you want to do like a parallel 4 with data parallel, just do work over my entire array, parallel reduce, where you need to kind of reduce down or scan. Then you have your execution policy, which, what range do you want to go? What teams do you want to work in? Or are you passing in a test graph? So I'm going to go through a simple example to give you an idea of what Kokkos looks like if you're not familiar with it. So this is an example. It's a simple iterative linear solver. It's used in the Mini-FE proxy application, which is available also open source. There's 3 math operations that are going to be used: a vector addition, a dot product, and a sparse matrix vector multiply. So first off, we've talked about data management. Uh, this is where kind of you get a little higher level with Kokkos. So you're going to have these views. They're Kokkos views. And then within them, so if you're not familiar with C++, you have these kind of brackets. And inside here, this is your template policy. So this is saying give me a double pointer in the host space and it's unmanaged memory. So this will be our host X array. It's going to be how many number of rows we have, and we're going to pass in some input to fill it with. Then we're going to have another view. This is a view pointer. This is going to be on the device. And this is going to have the same number of rows, and we're going to give it a label, X. So this is kind of what plugs in with those profiling tools. Because the one kind of downside with these template libraries, we have a portability level sitting on top of the other programming languages, is that the templates get very nested very quickly. But kind of bypassing this, you have some kind of labels like this where you can easily access and understand the output coming from it. Then we're going to perform a deep copy. So this is saying set it to the device from the host. So this kind of matches up with like allocate a host array, allocate a device array, copy it over. So for the actual computation, it's a simple data parallel loop using Kokkos parallel 4. This is easy to express in most programming models. It's kind of a good first example. It's bandwidth bound. So just to easily wrap your head around it, here's the serial implementation. We're going to just loop over our array and do our computation, store it in the Z array. So in Kokkos, you're going to see it on the bottom. So there's several differences here. First off, you have the parallel port pattern. So this is a parallel 4, just saying that this loop is in completely parallel, no dependencies across iterations. You have your string labels for your profiling and debugging. This lets you know like what kernel you're running with. Your execution policy. So this is saying how many iterations to do here. And this is the iteration handle. That's the integer index that's going to be accessed into here. So the other difference being that the loop body is now accessing the arrays through the parentheses. That's because the arrays are not pointers anymore. These are now Kokkos views. Otherwise, the loop body looks pretty much exactly the same. So the main changes are you're now using views, and then you got to change your 4 to be a parallel 4 and pass in this lambda, which I'll give a little more detail on. So for Kokkos parallelism, the simple usage is straightforward, similar to OpenMP. The advanced features are also pretty straightforward. As I mentioned earlier, the 3 common data parallel patterns are parallel 4, parallel reduce, and a parallel scan. You kind of put it all together. The computation is characterized by the pattern, its policy, and the body. So the body is the work. The pattern is what kind of parallel work are you doing, and the policy is how you want to execute it. So as far as the body goes, you provide the computational bodies either as functors or lambdas. So if you're not familiar with C++, let me give it like a little bit of brief introduction here. So the lambdas, you saw these also in SYCL, so it gets supported there. It's essentially nameless functions. So for our parallel 4, we're passing in our string and our size, our policy. Then you have this capture. This is saying capture everything by copy. And then you pass in the parameters. So this is the parameters to this function that opens with the break bracket and gets closed later. So this is your body to that function. So really the parallel 4, the third argument taking in, is a function. And the other way you can do that is by writing out your function as a functor. So here you're declaring a struct. This can just kind of live wherever you need to. And you're going to overload you're going to implement the operator parentheses. And then this is going to essentially be the same thing as your lambda above, except now you're using kind of local local variables. So you're going to see these all the time. So the nice thing about the lambda is that you're going to have the kind of body implemented directly in place wherever you're calling it, whereas the functor allows you to kind of keep things more simple. Now for memory management, data stored in views. They're pointers in a way to a multi-dimensional array residing in different memory spaces. So the views abstract away platform dependent out location and gives you automatic deallocation and access. So heterogeneous nodes, you're going to have one or more memory spaces that you're going to use, and then you can use mirroring to get performant access to views in host and device memory. So just a super basic example here, we're going to create a view array in the device memory space. So we're going to say that we're going to use this view type as a double pointer, and its space is going to be the device memory space. So we declare it. This is our first view. Now we want to create a mirror view. So this is going to be a host mirror, and it creates a mirror of the device memory. So now we can fill the host view with the input, copy the view from the host to the device, and then we make use of it and copy it back, much like you do with the other program. Okay, so that was a very brief introduction to Kokkos. We're going to jump into a bunch of the examples available through the Kokkos Fund project. So we're going to be using these Kokkos tutorials. If you just search Kokkos tutorials, you're going to find this GitHub. It's also available in the README. And this is kind of showing what you would do on Aurora. So on Aurora and Polaris, we have Kokkos built for you. It's available through our module systems. Once you kind of load it, you're going to have this Kokkos root set, which will kind of point CMake or whatever you need to find it. You can also build it yourself fairly easily. There's instructions on getting started for Aurora. And inside here, I'm going to go through, there's a bunch of exercises which have a beginning and a solution. So these are actually meant for you to kind of work through, and there's things you need to fill in. So it's a good learning tool. So I'm going to walk you through kind of how to get these going. Some resources here. Just going to leave this up for a minute. Just tell you what's available. So I mentioned the tutorials. That's what we're going to start taking a look at. We're going to look at the code inside of them. Then we have the lectures. So these are a bunch of videos on every topic you might want to look at with Kokkos. Then you have the documentation available through the Kokkos org, and the GitHub is always a good place to go, looking at issues, even closed ones if you're trying to find a solution to an issue. For running on Aurora, we have a dedicated page for Kokkos for Aurora and also on Polaris. And then I put in here the running jobs on Aurora, which I'm hoping everybody has been able to do by now. Then, of course, if you need any help, so there's the ALCF help. Kokkos has its Slack, and then, of course, we have the workshop Slack also. Okay, I'm going to switch over to the terminal now. Okay, so I'm set up here on a compute node. I'm going to be working on Polaris because we don't have access for Aurora right now. But for the most part, these are, it's a portable programming model. You're going to be working with Kokkos directly. It's really just what it's running as underneath. So there'll be a little bit differences in getting the modules set up and everything working. But once it is, the Kokkos code that you're writing should be pretty similar, unless you're intermixing it with that underlying programming model. So we'll show you an example of as we work through this. So I've flown the Kokkos tutorials here. And then inside here, there's a bunch of exercises. Let's start with the first one. So when you go into each exercise, there's a beginning and a solution. So here, if you look inside, it's going to kind of tell you what's the goal of this. We're going to just implement with a parallel reduce. So first thing first, you're good. The login node for the source code. So we're going to include this Kokkos core library. So this is kind of the main introduction to where you get those the implementation of Kokkos is by including this file. This is the Kokkos core, so it's your main GPU programming. Then it implements a lot of options for you, but then you're going to get down to here where the exercise is. So this is really basic introduction. You should be able to work through this pretty quick. It actually is giving you quite a few answers here. You're just tracing it, but this is what you need to do to kind of get your application started with Kokkos. We need to initialize the Kokkos runtime and encapsulate everything in between the initial and finalized calls inside of it. And then we want to convert some of our loops to use Kokkos parallel 4, parallel 4, parallel 4. And then we're going to do a parallel reduce. There's also a Kokkos timer, so there's robust support in Kokkos. And get that all implemented. Finally, we need to finalize. So this should be pretty easy to work through. And I'm going to work through it very quick by going over to the solution folder. So now we're uncommented here. And you can see where we implemented our parallel reduce and our parallel 4s. And it should be good to go. So over here on the compute node, there's instructions for this on the getting started, but switching to the GNU environment, using the NVIDIA mixed and loading in the Kokkos. So now I have Kokkos loaded. And the Kokkos home is set. This is being provided by default on the compute nodes. So we're going to build this. So this is our first Kokkos example. Run the exercise, and great, it worked. Now we're kind of curious, how did it work? See, we're not actually running on the GPUs right now, because if we looked in that example, we didn't really use the views. So the Kokkos views weren't being used, so we have no data there, so we're not running on the devices. So let's move over to a more interesting example. I'm going to jump to the third example. And we can take a look at it. And this will be actually implemented to run with the GPUs. So again, we're including our Kokkos core, but this time it's starting with that. But our goal here is to define device views, get up the mirror views for the host, and initialize those host views and do the copy to the device. So if you start looking through, all right, we need to use the allocate Kokkos views for the device. We're going to create mirrors and build them on the host. Then we're going to do deep copies to get the memory over to the device. Then when we run our parallel reduce, it's going to run on the devices. So let's take a look at what this is going to be once you implement it. I do think it's worthwhile actually working through these. So we're implementing our Kokkos views. So these are going to be of various types. So you have matrix type and 2 vectors. And then we want to create a mirror view. So we're going to use this naming convention of h underscore for our host views. Create a mirror view of each of these. Initialize the host view for all of our matrices and vectors, and then perform our deep copy. So here we're just copying to the device views from the host views. Then we're going to run our parallel reduce, which is going to, so just real quick to show you about lambdas here. So now we have a second argument for this reduce. This is going to be the variable which is getting reduced. spawn. So it's the update using this plus equals, and then where it's going to get stored back out as a result. Okay. So we're going to build it again. Okay, so we're running, but again, we want to wonder, okay, did we run the GPUs this time? Let's see. So we're going to use the profiler. So the nice thing about the portability layer is that it allows you to use the tools that kind of work with the underlying programming model, because when it gets down to it, that's what's actually being run. And now you see we get a lot more information. We're getting a lot of CUDA APIs calls, and then there is a Kokkos parallel launch. So this is a parallel reduce. So this is taking 99% of the time, and that is our one parallel production that's happening inside of our device. So now you see that we're running on the GPU. So there's many examples to keep working through. I'm going to show the next one I kind of want to go through was this multi-GPU with CUDA. So this is something we're able to use because we are on Polaris right now. Fun bonus exercise would be to take this on Aurora and make the modifications to get it to run with the sickle backend. So this is showing if you want to run with multiple GPUs, similar to what Abhishek showed earlier today. So we're trying to execute on multiple GPU devices, executing simultaneously. We're given a existing application, just some exercises that we need to fill in. So here we're going to use the CUDA API to access your devices and set which device to use. So you'll be able to do a similar thing in Sickle. This is also showing that with these portability libraries that you're able to kind of intermix them with the underlying programming model. The downside of that is you're going to lose portability, of course. The plus side, if you're coming from a CUDA programming model, that you are able to kind of incrementally implement the porting over to Kokkos and test it as you go, because the CUDA code will still work as long as you're running on the CUDA end of the device. Okay, so we're gonna set up an execution space. That's going to be like which GPU do we want to run with. Launch the team policy. You're going to need to tell it which device to run on now. So as we have here, this is going to work with a single device by default. So you need to create the CUDA streams and then allocate on the corresponding devices. And you need to set up the correct result type. Then you'll pass those into the operation, which was shown up above, which is doing the actual parallel reduce. And we'll be able to see the results from that. So let's take a look at what this is going to look like when it actually gets implemented. So one thing here is we need to use a Kokkos view for the reduce type. So the result type previously was just a dump pointer. We want to use a Kokkos view because this will avoid fencing over all the execution spaces within Kokkos. So you want to make use of the Kokkos view basically for anything being used on the devices so that Kokkos is aware of the memory. We're going to get the number of devices. We're going to choose just 2 of them, even though we have 4 devices or 4 GPUs available, but the tutorial is just assuming 2. So we're going to use the first one and the last one. And then we're going to set the device for our little devices array and create a corresponding string. So now you see with the operation, we're passing in one more variable. It's this execution space. So that's going to be telling us which GPU we want to run on. And now, as I mentioned before, so the policy is going to be team policy, and this also is going to need to say what execution space you want to work on. This will enable everything to kind of execute in parallel across both devices. So we have our execution spaces. These are going to be the first stream and second stream. And we need to allocate on the different devices. So we're going to allocate on the first device for our first three our first three vector types and matrix types. And then on the second device, the rest of them. Again, we're going to use our Kokkos timer, so we keep building everything out. These are our new result type, and these are going to be allocated on the different devices as well. And we're passing in that execution space to the operation so that everything gets executed as we expect. So now we should be running across multiple GPUs. So if we execute, great, seems very fast. But how do we know we're using both the GPUs? So if you're on the profiler, this is going to take a bit longer because it's running quite a few operations. But instead, what we're going to do is just say, we're only going to make the first GPU visible. So now it's going to be using the same GPU for both of those operation calls. So this should slow us down. And you see we're getting about half the bandwidth now. So kind of another bonus challenge here, especially if you're going to get on Aurora next week or 2 weeks from now. Switching this over to Sickle and also or changing it to be able to use 4 devices is kind of a bonus exercise. Okay, I guess the next one I want to show is Kokkos kernels, which I'm going to talk about quite a bit. So Kokkos kernels is, throw up the slide real quick. So this is similar like MKL and BLOS. The one nice thing is that you get a kind of simplified interface. So the Kokkos kernel shown here on the right, it's because the views have all the size and stride information that's required, so it's able to provide a simplified view. The Kokkos kernels are implemented on top of everything like you would hope. So if you're running on Aurora, you're going to get the one API plus calls. And on Polaris, you're going to get the cuBLAS calls. And you can kind of call into these at the team level. So let me go back to the examples. Now the Kokkos kernels is a separate, it doesn't come with the Kokkos core that we kind of clone and gets built and installed on there. So I did build my own. So you can't clone it down. Obviously, you need to set it up to build correctly. It's pretty easy to get it built. It just needs to kind of know where Kokkos is. Obviously, if you want to get it built where it's using all the underlying math libraries, you need to make sure that everything gets linked in properly. So I'm going into the CG solve. So this example is set up to get you to learn how to use the Kokkos kernels. Um, we want to implement this basically to use our BLAS functions, our sparse matrix functions. So we need to include header files for the appropriate Kokkos kernels for BLAS and sparse matrix. So they're just kind of provided here. We need to get these included now, addition to the Kokkos core. So now we're in like a full Kokkos application and setting up our copies and our views. So jumping ahead a little bit, after we set up our device views and our host mirrors and got everything copied over. So now we want to implement our calls using the sparse matrix vector, copy it back over, and then implement with our sparse matrix vector again and our dot product. So these are kind of the exercises you can search for to work through. So we're going to implement quite a few of them, though they are kind of simplified calls, so it does end up being pretty clean. So now we're including all the appropriate header files that we need to be able to execute this or access our Kokkos kernels. And after we get everything initialized and copied over, okay, we're back to our exercises. Now we're going to be able to use the Kokkos sparse with the sparse matrix vector. So as you can see, this is a bit of a simplified interface if you compare it to some of the BLAS calls. Just was checking chat. Yes, you do need to do a deep copy just because if you're dealing with any kind of complicated objects, so that everything will get deep copied over. It's not overloaded for assignment to work. That way it'll just end up with two host views. Then as we move through, we see that our implementations are quite a bit simpler and everything is available. So this is just using Kokkos Plus. It's pretty simple. We're just inside the namespaces, which is another C++ feature, which I hope everybody is familiar with. So I have this built. So this is going to fail because it doesn't know anything about where Kokkos is. So a lot of mystery. Okay, so that was setting the CMake prefix path. So this tells CMake where to look for CMake files. So if we kind of show you where that was pointed to, it'll be a little easier off the few nodes. So this is our built out Kokkos kernel. So if you're looking to include, include files for all of the different available library calls and our library that we're going to link in. So now I was able to find that.
Brian, we have a questions about deep copy. They're asking why we have to do deep copy instead of just viewing.
Yep. So like you were hinting at, Orion, it is basically in case you have a very complicated view, if it's not just like a vector or a matrix and you need to chase pointers. So it won't end up doing a deep copy. If you just do the assignment, it will end up working kind of like you expect, where you just end up having two coast views instead of a deep copy for the data. So this is compiling. You're kind of seeing that takes a little bit longer. I'll just kind of give that as a note as you move a like full scientific application over to Kokkos. You can start getting larger compilation times. So on the getting started for Aurora, you're going to want to focus on getting things kind of compiled at compile time as opposed to JIT time. So there's instructions available on the getting started there. This is because with the C++ templating, everything gets a little more complicated and difficult to compile. It's going to take a bit longer. So if you try to be better to get everything kind of compiled ahead of time, as it specializes for what's actually getting built for your application. Okay, great. So now you see we're able to run. This is making use of all of the Kokkos kernels that are available. We're getting use of the cuBLAS libraries underneath it. So we're able to get some very good performance as we do a lot of computation here. I would run this through the profiler, but it ends up taking a long time because we do end up calling quite a few map library calls. Okay, so I think a little bit of ahead. Those were the examples that I wanted to run through, but I will switch over to this backup slide deck. So these are some of the slides coming out of the actual foundation. I wanted to talk about the tools. So I kind of mentioned this a few different times. And a lot of this is now fully developed. So there's static analyzers, debugging, where everything gets the Kokkos naming, and you can get cleaning up for your Kokkos code. So basically the Kokkos tools, they're setting up sort of third parties. So this is like, such as like HPC toolkit. You're going to learn about these futures. They have hooks so you can pass in the names, and then you can get kind of more useful information instead of giant template naming conventions. So you can see an example here. Uh, this is with Tau, where you get kind of things hooked in, so you can get those Kokkos naming conventions. So it's a lot easier to understand what's happening. And the quick example for the static analyzer. So you see, it's just going to get you some kind of information as you work in development. So you're modifying a reference captured value that is local. So this is using a lambda with this is saying capture it by reference instead of by value. With that, I think I'm going to switch to questions, running a little bit ahead of time.
Thanks, Brian. We do have a question on the Slack. I don't know if you want me to read it for you. I think it's just a command line missing. It's related to the examples that you went over.
Yep.
Do you see it, or do you want me to paste it in the chat?
Yep, I see it. So this is using the provided script, which I was just running through. I'm guessing that you have a error showing up from that run install lib cmake. I was able to just run it myself, though my environment's probably different from yours. So your make file didn't get generated because the cmake most likely failed during configuration. If you're able to share that, I'd be able to help with it.
Just as a note, for the Polaris, they do have to load the CMake module, right?
Yeah. So to get set up running on Kokkos, there's a few different things you need to do. So you need to load the SPAC-P base so you can access CMake. Then you need to switch from the programming environment GNU. So I restore back to the base mod. Sorry, I'm not sharing my screen. Am I?
Yeah, no, I was wondering if you're doing that.
Okay, so I just ran module restore. This is going to set me back to the default. What's loaded. So we need to load in. We need access to CMake and Kokkos. So we're going to module files. Load SPAC-P base. From here, we can get CMake. Then we need to swap the NVIDIA programming environment for the GNU one. And I've been doing the mix, so it seems like this is getting deprecated. And from here, we can load Kokkos. And now we have our Kokkos helm set up. So this is built in for the CUDA backend. With the toolkit. I think one other thing that you probably hit here is need to switch the native GCC to a slightly older one, just because the CUDA support tends to run a little bit behind GCC, so it would complain about 2 kilobit GCC. We'll go back to our example running with the GPU. Let's build it at 4th time. So as you see, this is your CMake invocation, and it's telling you, oh, it found Kokkos, and it lets you know, okay, we have OpenMP, Serial, and CUDA built. So this is what provided. So you can write a Kokkos code where you're executing, let's say 4 OpenMP threads, each of which is using a different GPU.